In this tutorial, we're going to look at how we can create a raster elevation map from a series of discrete points of elevations. The goal is to produce something like this, a digital elevation model, or DEM. A DEM is a raster file in which all the pixels or cells have elevation values in them. Taken together, they produce a scene that allows us to visualize the behavior of the topography across a landscape. They also allow us to analyze how things like water will move across that surface. In order to create a digital elevation model, we need elevation data. Elevation data can be acquired in a lot of different ways. There are a lot of technologies that are used to acquire elevation data of the landscape. It can be done manually, going out into the landscape to measure elevation values using levels and surveying. We can acquire it using LiDAR, laser ranging, radar, or stereo plotters. So the data we're going to be using is derived from stereo plotting analysis. And essentially this process takes two images of the same patch of ground that are essentially identical but are offset just slightly. And that offset allows us to measure elevation. It works in a very similar way to the way our eyes work. Your eyes are in two slightly different positions, which means that whenever we look out at a landscape, we're always seeing things from two slightly offset positions. And that offset allows us to evaluate distance or depth. So imagine then we've acquired elevation values across some landscape at a variety of points. And so we have elevation values at those points, but we want to know about the elevations in between those points in order to create that continuous surface. So we overlay a grid on top of it, and we can see that some of the points fall inside the grid cells, so we have elevation values. But what about the cells in between? How do we estimate those values? Well, the simplest way is to do basic interpolation. In this case, we'd say, well, the value that falls midway between 12 and 8, for example, is likely going to be 10. We can apply that to all the other cells, so we can create values and then create a continuous surface, which we could then convert to a raster elevation model. In a GIS, though, we want to use a slightly more sophisticated process so that we can acquire as much information as is available. In this case, we would want to estimate the value of the target cell by using as much information as is available to us, all where we have known data values. What we're going to do, though, is we're going to use a process called inverse distance weighting, in which we take into account the distance of the known values to the target cell. And it works like this. Points that are closer to the target cell have more influence than points that are further away. And the way that we calculate this is that we take each of the values that are known, the known elevation values, and we divide them each by the distance they are from the target cell. We divide each, add them all up, and divide the whole thing by the sum of all the weights of all the distances, and that will give us our value. In this case, it gives us a value that's very similar to the rough approach we used earlier, but it's more precise. What we're going to be doing next is applying a similar process in ArcGIS to create a raster surface, although we don't have to go out and acquire the elevation data in the field. In this case, we're going to be relying on digital terrain model files, DTM files, that are provided by MassGIS, a state agency for the state of Massachusetts, which contains coordinate positions across the landscape which are accompanied by elevation values. We're going to create maps of these points, and then we're going to interpolate them in Arc to produce a continuous raster surface and ultimately clip this to the community of interest so that we can use it for later analysis.